Lesson 12.1, the goodness of fit test. The objectives for this lesson is to perform a goodness of fit test. Let's go over mutually exclusive. Mutually exclusive means that there are no outcomes in common. An example, a probability experiment is conducted in which the sample space of the experiment is S equaling 3 through 14. Let event E equal 4, 5, 6, 7, 8, 9, and event F equaling 8, 9, 10, 11. List the outcomes in E and F. So what does this event E and event F have in common? They both have 8 and 9 in common. So are they mutually exclusive? No, because they have 8 and 9 in common. So these are not mutually exclusive. Chi-squared, this is like an x squared, it's pronounced chi-squared. Test hypothesis regarding the entire probability distribution. So for example, if we want to test whether the distribution of colors in a bag of M&Ms follows the distribution stated by the manufacturer, we'd use a chi-square test. Okay, so this is for seeing if distributions follow a specific stated distribution. There are 4 characteristics of the chi-square distribution. Here you can see to the right a diagram. So right away you can see that it is not symmetrical, right? It is actually skewed right. We can also see that the shape is going to depend on the degrees of freedom. DF again is degrees of freedom. Okay, we've talked about this slightly in the past. To find the degrees of freedom, you take n minus 1, so your sample. Three as the number of degrees of freedom increases. It says the degrees of freedom increases, what happens? Chi-square becomes more symmetric. And then the last one, the values of chi-square are non-negative. You can see that here. Right, these are positive values, or greater than or equal to 0. So with chi-square distribution, we also have critical values, just like our z and t. And you can find these on the next page. The left column represents the degrees of freedom, and the top row represents the area under the chi-square distribution to the right of the critical value. We use a notation chi-squared sub alpha to denote the critical values such that the area under the chi-squared distribution to the right of chi-squared sub alpha is alpha. So unfortunately there is no calculator command for this, so you will have to use table 8 here, and it should be given to you on your homework problems. There should just be a link you can click on. So let's find the critical values that separate the middle 90% of the chi-square distribution from the 5% area in each tail. So we have the middle 90%. Okay, if they didn't tell us that the tails were 5%, we could have just taken 100 minus 90 and then divide by 2 to get what's in each tail. And we're assuming a 15 degrees of freedom. So the sample size, number of degrees of freedom, is equals to n minus 1. So if you wanted to find your sample size, you could have figured that out mathematically, and it would be 16. So the critical values are these lines right here. So here we have chi-squared. We want to know the area to the right. This alpha is the area to the right. So we have 90 plus 5%. So that's 95. And here we have chi-squared sub 0.05. Let's do chi-squared sub 0.95 first. We have 15 degrees of freedom. And then find 0.95, so 7.261. And then our other one is 15 degrees of freedom for 0.05, 24.996. And these should be in order, right? Smallest, largest. Remember, degrees of freedom is n minus 1. If the number of degrees of freedom is not in the table, choose the degrees of freedom closest to that desired. If the degrees of freedom are exactly between two values, find the mean of the values. So let's say we had degrees of freedom of 95, and we had to the right 0.995. What you would do is you'd add these two together and divide by 2. That's what it means by this last sentence.